All right, so I'll get started. Begin with a with a verse of scripture here. So this is, let's get my phone to behave. Where'd you go? This is Habakkuk, chapter 2, verse 14. It says the following: "For the earth will be filled with the knowledge of the glory of the Lord, as the waters cover the sea." This is Habakkuk 2:14. I'll begin with a word of prayer. So, Heavenly Father, we thank you again for this opportunity we have to meet, to study your creation. Just pray you'd be glorified at what we do, that we'd understand a little bit more about your creation together, and that students would ask good questions as they think of them, Lord. You know my prayer, Lord Jesus. Amen. All right, so without further ado, let me do some examples. So we will continue illustrating Newton's laws today. So let me start out example 1 here. Suppose you got a car and it's going around a track, all right? Imagine that's a car. All right, so the car is going around a track, and this is a flat track. The radius is r, all right? And let us suppose that the track is circular, all right? Furthermore, you have a force of friction, right, which is equal to, mu k times the normal force. So of course this is kinetic in this case. Well, to be fussy, it's not really kinetic. Let me just say mu times the normal force. To be totally honest, rolling friction is a more complicated thing that I'm not going to completely describe in here. You can read your book for more on that, right? But if the wheels are actually not spinning, then technically it's actually like a static friction, because the wheel is just rolling without slipping. So it's not actually kinetic friction case. But anyway, the force of friction is mu times Fn. Now, then the question is, and let's suppose that this car here has a mass of the car. Listen to me. Car is equal to m. All right. Then what's the situation here? Now, what makes the car go? There's also some sort of force that the tires put on the ground, right? And I suppose that's actually what the force of friction amounts to, right? The car turns the tires, and the force of friction is what makes the car go. Like if you have a completely frictionless track, then nothing much happens, right? So, all right. So what goes on here? What's the free body diagram? We've got, on the one hand, the normal force, like so, right? On the other hand, we've got mg downward, right? And then what direction does the friction force point? Backwards.
Well, if it's the force and the power, would it be going?
I mean, it's the force which makes the car go. So I guess the question is which way is the car going, right? So here's a particular case. If we're going in constant velocity motion, the force of friction would go something like this. All right? And so let me draw a picture, top down. So here's the car. Force of friction would be something like this, tangential. Right? I'm assuming constant speed for the moment, all right? Oh, excuse me. That is exactly wrong. Why is that wrong? So you guys tell me. The acceleration, that's right. So we know for circular motion that the net force is what? mass times the acceleration, right? But we also know for circular motion that that's equal to mv squared over r with a, let's say r hat, well, whatever notation you want to use here. You know, we could say minus r hat if you like. That's center seeking, right? Now this again assumes constant speed. Constant speed, this is the case. Now, if it's not constant speed, then the acceleration doesn't have to be center seeking, right? But in the constant speed, so my picture's wrong. Where force of friction actually goes where? It should do what? It's got to be the force which actually causes the circular motion. So the force of friction is actually center seeking here in this case. Okay? My bad. Sorry about that. There we go. Fixed it. Okay, so what's the story here? If we're constant speed, circular motion, pretty simple. What's the equations involved here? So we have the normal force has to be equal to the gravity, right? If there's nothing else going on, like I'm not adding some kind of spoiler. I could add like a spoiler to the car, right? Add additional downforce or something, but none of that stuff. So just gravity here is the normal force, and so the force of friction is what? And so we're going to assume that it's like we're going to be in the case. We're going to be in the case that we're maxed out. All right, like this is the maximum speed you can get away with for this radius. So we're at the maximum of the friction, which is just mu times mg. All right, and so this would be minus. Well, let me just get to the point here. So what we got is mv squared over r is equal to mu mg. All right. So in this scenario, we have the following relation, like the speed, the max speed would be what? The m's cancel, and it looks like we've got the square root of mu gr, I believe. Because the m's cancel. All right, so let's put in some numbers just for fun. What if your mu is, say, 0.7, and well, of course, we know what g is, right? So, but let's suppose that the radius is like 50 meters, just for the sake of discussion here. What would the max speed you could go around such a turn be?
18.52.
I got an 18.52. Anybody else agree? Cool. Now, can you guys tell me that? What's that in miles per hour? Oh man, I just hit the cube root. What did you guys get? You just told me. 18.5? Okay, cool.
I did 107.30.
107.30 miles per hour? That feels wrong. All right, so I can take 18.5 and divide by 1609. That's the number of meters in a mile. And then I think I have to multiply by 3600. I get 41.4 miles per hour. Yeah, 41.4 miles per hour. So that's not an unrealistic thing to encounter, right? Like a turning radius of about 50 meters, you know. The coefficient of friction between a lot of roads and your tires is about 0.7. Like that's not unrealistic. What happens when it rains? New rain is more like 0.2. And if you keep the same radius, what's your maximum speed then? It's not as good, is it? 0.2 times 9.8 times 50. square root that thing. So I got 9 point Vmax of like 9.9 meters per second, also known as how many miles per hour? It's about half of that, right? So approximately 20 miles per hour ish. So this is why when it's raining, do not go as fast. Because just because you can make a corner when it's dry, it does not mean you can make that same corner when it's raining, right? Because the rules of the road have changed, right? The road is way slipperier when it's raining, as a general rule. Any questions about this? Now, I'm assuming through this whole derivation that we have constant speed, right? Constant speed means that the acceleration is pointing directly towards the center of the circular motion. If we don't have constant speed, so example 2, you could have something like this. Again, motion around a circle, radius is r, all right? And we'll keep it at 50 meters, just like the last calculation we did. And I'm going to let the velocity at this time be, let's make it 10 meters per second, since we know that's at least plausible, all right? Then my question is, if your speed is 10 meters per second around a radius 50 meter track with your coefficient of friction being 0.7, all right? Then the question is this: what is the maximum dv dt possible? In other words, how fast can you be speeding up at that point? All right? So how does this work? So in this situation, your acceleration is not center seeking, right? If you're speeding up, there's two pieces, right? As we derived, the acceleration has got two pieces, right? It's got your dv dt piece, which is tangential, and then you've got your v squared over r piece, which is normal. So those are the two different components to the acceleration, which would be something like this, all right? So the two pieces to the acceleration, if it's non-constant speed, are the tangential and the normal, or if you like, center seeking. So the center seeking, we were just studying the last example, that is your a sub n. Over here, you've got your a sub t, the tangential piece. Now these are perpendicular, right? So the deal here is that a squared, well, a is equal to the square root of your tangential acceleration plus your normal acceleration. Now, specifically, that is the square root of dv dt squared plus v squared over r, quantity squared. So in this situation, the friction force is pointing in the direction of the acceleration, but it's not center seeking, all right? So like the friction force, if we were to draw it, would be, let me choose a different color. The friction force would be pointing in the direction of the acceleration, all right? But only part of that center seeking. I'll make it bigger there. There's your friction force, something like that. Now the magnitude of the friction force, we know what it is. So ma is equal to mu mg still. Because we still have, in this situation, same as the last example, that the normal force is equal to mg. So the force of friction is mu mg, and that is, of course, the net force here. So I have ma equals mu mg. Yep.
Does the friction force always point in the direction of acceleration?
In this situation, yes. In general, no. Yeah. So the friction force is what keeps it going in a circle. That's why it has to point in that direction. There's nothing else that can supply that acceleration but that friction force. So it's like inescapable. Well, unless there was like a rocket or something, right? But yeah. Or maybe it's a hovercraft. I don't know. Okay, so ma is equal to mu mg, which tells us that, well, a is equal to mu g. That's like the max we can get. This is the maximum acceleration that's possible, right? This is the maximum case. And so this would be equal to the square root of dv dt squared plus v squared over r quantity squared. We have everything here, right? Except for one thing, which was we don't know. We solve for dv dt. We get dv dt is equal to the square root of mu g squared minus v to the fourth over r squared. Whatever that is, that's the maximum amount you can accelerate. That's how fast you can speed up at that point, given these conditions. So what you got here, square root of 0.7 times 9.8, meters per second squared. You got to square that thing, and then you got to subtract from that 10 meters per second to the fourth power, yowzers, divided by 50 meters squared. So whatever that works out to. Well, I don't know. What are we at? 0.7 times 9.8. Square that. Subtract 10 to the fourth divided by 50 squared. I get 43 under the square root. I get 6 point, come on. I got 6.56, and this feels wrong to me, 2 meters per second squared. Am I right? Do you guys get anything else? What'd you guys get?
Under the square root.
Yeah, but
More like 63.
you got 63 under the square root. Anybody else? No one else is participating. You guys are just waiting for the 3 people here with calculators to do stuff.
I had 43.1.
What's that?
I had 43 in the square root.
43 under the square root? Okay, that's what I got.
Same answer as we said.
Same answer? Okay. Well, it's a consensus then. Sorry, Gabe.
Oh, wait. Oh, I didn't square them.
Oh, okay, good. Cool.
Yeah.
So that's actually, I was surprised at that much, because the reason I'm kind of surprised is like the max speed we figured out in the last problem was what? 18.5? So I was thinking it would be less because, theoretically, if you just think about it, just forget about circular motion for a second. Just think about like straight line. The maximum friction force is what? 0.7 times the weight? What's 0.7 times 9.8? It's 6.86. Man, that is just, how is it that close to that? That feels so wrong. I mean, we worked it out, but what's that? For this? What did you use for G? 9.8. Well, that's weird. But you got 6.5.
Yeah.
Okay. And that's 3, sorry. Anyway, numerical bemusement aside, this is how you work these kind of problems. The acceleration has 2 parts. It's got the tangential part, it's got the center seeking part. Center seeking part, non-negotiable. If you're going in a circle, that has to be there. The tangential part depends on whether or not you're changing speed. If you're going constant speed, the acceleration has to be directly center seeking. Game over. On the other hand, if you are speeding up going around, then you can have this tangential piece. The magnitude of the acceleration, again, is the square root of the sums of squares of these, because these are perpendicular, and that's how we add the length of perpendicular vectors. So there's that. I'm going to move on here. Example 3. So let's suppose we've got a box here with mass. Let me make it bigger. A box here with mass m1. And then I've got another box here. I'm going to regret drawing it so close to the top of the whiteboard. Oh well. M2. All right. And then, just to make things annoying, let's suppose that on the one side we have Mr. Top Hat pointing on it with a pointy stick horizontally with a force of F naught. Boop, boop. And then over here we have an evil cat pushing on it this way with a force of F1. All right? My question then is, what happens? Now, for the purpose of this, we're going to assume that the, just to keep things a little bit uncluttered, let us suppose that there's no friction between the boxes and the plane. All right, so imagine that the boxes and the plane are, you know, like both made of something super slippery. But in order to make this still make sense, we're going to assume that Mr. Top Hat's shoes are nailed to the ground, and as well the evil cat has been screwed to the ground. So that's how they're staying fixed, and they can do this pushing despite the frictionless interface here. Okay.
Hey, Professor?
Yeah.
Since this is physics, I think we should say they're slime blocks.
They're slime blocks?
Minecraft slime blocks.
Minecraft slime blocks. See, that's outside my world. I don't know about that. I you know, it's after my time. We had no mind. I had to play with actual Legos, so you know. And you didn't. Fair response. All right, so question then is what happens? So there's a few different things going on. All right. So the vertical, what's going on vertically is kind of uninteresting for this problem. So like vertically, if we think about this one, there's the normal force on the first one, and you've got gravity force m1g down, right? So there's that. This one, you've got the normal force going on the second one, and you've got m2g down. Now that's kind of it for the vertical. We don't really care much about that, right? They just equal out. It's not really the interesting thing here. What's interesting more is that there's a new force in town. There's the contact force between these two boxes, right? So the contact force says that basically you've got the contact force going this way. We could call this the force of 2 on 1 goes that way, but also the force of 1 on 2 goes that way. And let me just unclutter my picture and draw M1 as if it's just on its lonesome down here. All right, so like on M1, we have F naught from Mr. Top Hat, but we also have the force of 1 on 2. Yeah, thank you. I should have just called this thing C, and then I could have saved myself from that. But thank you. I do appreciate the correction. Force of 2 on 1, of course, right? And this is M2. On the other hand, if we look at, come on, seriously? Good grief. M1. M2. Over here, we've got F1 going that way, right? And we've got what? The force of 1 on 2 on this one. Now, I don't know about you, but I'm very tired of F of 1 on 2 and F of 2 on 1 as labels. They're very much, I just don't like those labels at all, do you? Okay, so what I suggest is we give those a simpler name, like this. The force of 1 on 2 is equal to C. And that is equal to the force of 2 on 1. Now, why can I say this? This is Newton's third law. See, the contact force are a third law pair. There has to be an equal and opposite reaction. Another way to imagine this yeah?
Is that because you're assuming that these aren't moving?
Oh no, they could be moving, but they're not deforming.
Okay.
So the net force at the point of their contact has to balance out, is another way you could understand it. But usually we just say they're a third law pair, so they have to be equal and opposite, which gives me, in short, that the magnitude of this one is C, and the magnitude of that one is C. Even though they're pointing in different directions, they have the same magnitude, right? Does that make sense? I hope. So then we can write Newton's law. Now they're stuck together. They do share the same acceleration, whatever that is, all right? And so here's what goes on. We've got m1 times a is equal to, which way do you guys want to make positive? Right? Okay, good choice. F0 minus c, that's m1 times a, m2 times a. And by the way, I'm completely ignoring the vertical here. Why? Because it doesn't affect the horizontal motion. The vertical and the horizontal are decoupled. How could that change?
There's friction.
If there was friction, then we'd need to think about it a little bit more. Friction would give us a normal it's still, I mean, the vertical forces, the vertical equations would still just be Fn equals to m1g, right? To make it more interesting, I could do something like Mr. Top Hat pushes it at an angle. Then you'd have to decompose the pushing force into the vertical and the horizontal and take care of that like we did last class. So you could look for that flavor variation if you wanted to. Now the Newton's second law on this one, we've got m2a equals to, by your request, right is positive, c minus f1. So there you go. These are Newton's laws. Now you got two equations and you got, well, two unknowns, right? We don't know the acceleration and we don't know the contact force. We'd kind of like to know both of those. Two equations, two unknowns. How should you solve them? Make them equal to each other is one option. There is a lazier option here. What should I do to these equations? Make them equal to each other is a perfectly good answer, but I'm looking for something lazier here. Still not lazy enough. Still not lazy enough. You just add the equations. This is something you can do. Don't tell the other math professors. So I'm just joking. Hopefully they believe in it too. So m1 plus m2 times a is what we get from adding the left-hand side to the left-hand side, factoring out a. And on the other side, the c's, they be canceling, and you just get what? F0 minus F1. Lo and behold, the acceleration is equal to m1 plus m2 divided by, oh, wait a minute. I better think about my life. I'm tired, guys. All right. F0 minus F1 divided by m1 plus m2. That probably would make more sense, right? So there you go, that's the acceleration. Now some of you who have some kind of innate intuition about mechanics probably could have told me that without doing all what I did, right? You probably could have ignored even the concept of the contact force and just said, well, what you're really looking at here is like a single mass. It's essentially the same thing. If I just got one big mass, the mass is equal to m1 plus m2, right? And then that force on it is what? You know, it's got like F1 this way, and it's got F0 that way. That's pretty much it. And so, yeah, of course, the acceleration is F1 F0 minus F1 divided by the mass. That's the acceleration, because F equals ma, right? You'd be right. What concept are you using there? The concept you're using is something called the particle model. The particle model says that you can treat a composite system as if it's a single mass, concentrated at the center of mass, which is something we need to work out more formally. For now, your intuition's not wrong. However, your intuition also will not help you answer the question of what the contact force is. What's the contact force? See, I can figure it out because I wrote down Newton's laws, and now I can do algebra and solve for C. So pick your poison, whichever one you like. We'll solve the second one for C. That gives me C is equal to M2A plus F1, which is M2 times F0 minus F1 divided by M1 plus M2 plus F1, also known as M2 times F0 minus F1 plus F1 times M1 plus M2. I'm starting to run out of whiteboard here. Divided by M1 plus M2. I think something will be canceling. Maybe not. I've got an M2 F1 and I've got an M2 F1. So I think these two terms here cancel. And it leaves me with M2 F0 minus, plus M1 F1 divided by M1 plus M2. So there you go. That right there, my friends, is the contact force. In short, do algebra, solve the Newton's equations for them. You can find them. What happens here? So let's think about some special cases, right? What would be a special case? How about this? So here's a special case. M1, I'll get out of the way in a second here. M1 equals M2, right? And how about F1 equals to 0? What happens in that special case? Does it make sense? So we're just pushing, Mr. Top Hat's pushing, but that's it. Yeah? Yeah, no friction still. What's the acceleration in that case? So acceleration's just, F0 divided by 2m, yeah. Yeah, let's call that m. And what's the contact force? So F1 is 0. You've got m over m plus m, also known as m over 2m, also known as a half. So the contact force is 1/2 F naught in that situation. So that's what happens. So when you push on one box with a force of F naught, it doesn't mean that the whole F naught force pushes on the next box is one way to think about this, right? Just a half of it pushes on the next box if the boxes have equal mass. However, if the boxes have unequal mass, it's a different story, all right? So, like if the mass 1, let me look at this formula here for a second. I'll write it here. So like let's stick with the F1 being 0 for a second here. The contact force is like what? It's M2 F0 divided by M1 plus M2, right? So like, suppose F1 equals to 0 for the sake of discussion for a bit here. What happens when the mass of 1 is much smaller than the mass of 2?
More force has to be used for the second mass.
Yeah, like, well, most of the force goes on, the contact force is almost the same as F naught, right? Like if M1 is super small compared to M2, this just essentially is F naught, right? On the other hand, if the other way goes around, if the mass of 2 is much smaller compared to the mass of 1, then the contact force is very small, comparatively speaking. So like here's the kind of two situations you could think about. If you can imagine this. It would be better if I had a box in here, but maybe a box? No? Yeah. So if you could, well, let me just use this as a box. So if you can imagine, like, here, use my cell phone. If I have, right here, if this is M2, right? And I put the M1 over here, and then I push here, most of the force goes here, and just a tiny bit pushes on the cell phone. Conversely, if I push on the cell phone, most of the force is goes on the cell phone, and then just a tiny bit of the contact goes on to the larger mass. If these had like equal mass densities, you could kind of think about this with like a loaf of bread or something. Like if you push on one side of a loaf of bread, the pushing force is mostly close to where you push, right? And as you go further in the bread, the contact force of slice on slice on slice on slice decreases. You could do this with, instead of 2 boxes, with like 3 boxes. You could study the contact force between not just 2 things, but like 3 things. Then you'd have 2 contact force pairs to think about, and you could go through this as well. That problem is already solved in my posted PDF, handwritten stuff. I don't think, typed that up yet. I'm not sure I will. Anyway, so Newton's third law. Let us go on. If I can find my phone. Oh, here it is. Oh, lest I forget, your exciting attendance sheet for today. So it's time for pulleys to enter the scene. Let's talk about pulleys and ropes and such. So I've been doing pushing with just like little, dudes pushing on the box. But oftentimes we like to attach a rope to something, and we like those ropes to go around pulleys. And the rules in here, for the moment, is that the rope doesn't stretch. It's unstretchable rope, all right? And the pulleys have no mass, which means that they don't have any resistance to the rope, like going around them. So the mass of the pulley and the mass of the rope, for the most part, doesn't play a role in most of the problems we set up, at least for the start. And that, of course, is an idealization, which we will make less ideal later. Like, we'll actually look at massive pulleys. On occasion, we look at a massive rope. So we'll get to that. But for now, the ropes are essentially massless. And here's one. So I'll keep it relatively simple. Suppose you got a tabletop. You got a mass here. But I'll add friction to the mix to make it interesting. So let's let this have a coefficient of static friction of 0.5, let's say. All right. And there's a pulley over here, and there's a rope that attaches to the pulley, another mass hanging over the edge here. And we'll call this mass M1. We'll call this mass M2. Then the question is simply, what's the acceleration of such a system? All right. Or I guess you could ask the question, does it even accelerate? I mean, does it move, right? So let's think through this. How do we do this? Okay, so we do Newton's law on each mass, right? And so like for M1, you got the normal force, Fn1. You've got gravity, m1g acting down. But there's a new guy in town here, the tension force. And the tension force is going to pull in the direction M2 is pushing. Right? So like it goes this way because M2 is pulling down. So the tension force is like this. So we're going to call that T. T for tension. Tension is a part of a third law pair transmitted by the rope from one mass to another. Because the rope does not stretch and because there's no mass to the pulley around which the rope is going, that means the same tension. It comes this way. All right? Now the rest of the free body diagram on M2 is kind of boring. It's like so. All right? It's just the gravity M2G. There is one other player in this game. What's that? Static friction, right. I guess it could be kinetic if the thing is moving, but you know, let's figure that out. So yeah, force of friction goes this way. Now the force of friction is specifically equal to, let's say, mu times the normal force, right? But we can see from the Newton's second law, the vertical balancing of forces there, on the basis of the fact that m1 is sliding along this horizontal plane, right? The vertical acceleration is 0. Logically, it must follow that Fn1 is equal to what? It must be equal to m1g, right? Otherwise, there would be a net force vertically on mass 1, which would mean that either the box is accelerating into the table, which would definitely mess up the finish, or it would be flying off, which would be weird. So sticking with mass sliding on the plane as is given, we get ourselves a mu m1g for my magnitude of the force of friction there. All right, so let's write down Newton's laws. On m1, we have m1a is equal to the tension force minus the force of friction. But what was the force of friction? It was mu m1 g. And let's see here. I mean, that's the maximum force of friction, right? Assuming mu is the static one. And then what's Newton's law on m2? I think I said something cagey about, you know, it's nice to make upwards positive except when you can't. We've come to that point now. I made a choice, which was to make acceleration positive in the right direction, right? By writing that first equation, I said t, I put a plus on t. That makes t pointing in the positive direction. So positive motion is like that. The string not stretching means that the acceleration on m1 is the same as the acceleration on m2. m1 being horizontal, m2 being vertical. So we're stuck with it. We're stuck with the fact that downward is the positive motion, positive direction for A as we've set up the horizontal equation. In short, I must write m2g here minus t. And because I'm tired, I'm just going to assume the thing is sliding. Okay, so let's think of this as being kinetic friction. I guess we could, well, you guys tell me, what would the situation be? If it's not moving, what would, fine, let me think about it. If it's not moving, what's the situation? Let's talk about the static case.
Acceleration is 0.
Acceleration is 0.
Or t tension equals mu times F1 times g.
Right.
And t also equals mt times g, therefore.
Now, hold on just a second. So t is, you're not wrong, but I would point out that one of these things is not like the other, all right? Like the tension being m2g, this is non-negotiable in the static case. Now, is the tension m2g in the non-static case? It's not. When the thing's accelerating, the tension doesn't have to be equal to m2g. It's just not the case. Tension being equal to m2g presupposes the acceleration being 0. See, this being 0 is what's required for m2g to be equal to t. If acceleration's non-zero, that tension doesn't have to be that. But if it is in the static case, you're right, t2 is m2g, and that forces us, you know, so the tension here is less than or equal to this, right? That's the thing. That's the maximum force of static friction. Remember, static friction is technically defined by an inequality. That's the maximum. And So I guess what we have, the question is, can we solve this inequality? So if we just divide by g, what do we got? We've got m2 has to be what? Less than or equal to mu. I guess I should be putting an s here, right? My bad. So what's the situation here for this? As I set it up, if mu s is actually 0.5, what's the maximum mass you can have hanging off here before it starts sliding? Twice m1. It goes the other way around, doesn't it? This is 0.5 m1, right?
Yeah.
So m2 has to be less than half of m1. Because with the coefficient of friction being a half, you at most get half the weight as a friction force. Okay? That's the static case. That's the answer to the static case. Okay, so let's stop with the static case. Start with the kinetic case. The kinetic case. Kinetic case, A not equal to 0, right? Kinetic case, so I think we could say what? M2 greater than 0.5 m1 would put us in the kinetic regime, right? If the second mass is more than half the first mass, it's fallen, right? It's fallen down. I'm assuming it like starts from rest just for the. I'm not going to do some kind of weird thing like I start this with this thing going up like that and that thing going over that way or something. Like no. Starts from rest, falling down. So then my question for you guys is, what's the acceleration? And how do you find it? We've got two equations and two unknowns. Starting to notice a theme here, yeah? What's that? I thought I heard something. No?
Add them.
Add them, yes. We have a winner. The same thing we did last time. Add these guys. We get m1 plus m2. A is equal to the t's be canceling. And we got ourselves a m2 minus mu m1. Factor that g out. And your acceleration is m2 minus mu m1 divided by m1 plus m2 times g. By the way, if we solve it with friction, we've solved it with no friction, right? What happens if there's no friction? You can put what? Just put mu equal to what? 0. And that tells you that the acceleration is m2 divided by m1 plus m2 times g if the acceleration, if there's friction, no friction. Does this make sense? I mean, okay, so we got to think about third law pairs for contact force. We need to think about circular motion has to be governed by v squared over r. And now we've got ropes and pulleys, so we can put these things together, but I don't put all of them together. At no point have I ever given you guys a problem which is about like a car on a pulley. I don't think so. Anyway, I think that's it for today, guys. So, I did post the solution. I would warn you, the last problem, it's tricky. It's tricky.